Welcome back to Computer Lessons.
File systems act as the primary translator between physical storage hardware and the operating system interface. Without these logical frameworks, a hard drive remains a chaotic sequence of raw binary data points. Every operation to save or delete a document requires precise coordination between the kernel and the storage controller unit. A physical drive consists of sectors representing the smallest addressable unit of magnetic or flash memory storage space. The file system groups these sectors into larger clusters to optimize read and write performance during transfers. This organization allows the computer to manage billions of bytes without tracking every individual sector address. The file system creates a hierarchical structure using directories and path names to keep data accessible for the user. It stores metadata, which includes the file name, size, creation date, and exact physical location on the disk. This metadata is essential for the operating system to retrieve information from the storage medium. FAT32 is one of the oldest and most compatible file systems still in active use today. Developed by Microsoft for earlier versions of Windows, it uses a simple file allocation table to track clusters. Its wide support makes it the standard choice for removable media like flash drives and cards. Despite its compatibility, FAT32 suffers from a significant limitation regarding the maximum size of individual files. It cannot store a single file larger than 4 GB due to its 32-bit offset architecture. This constraint makes it unsuitable for modern high-definition video files or large software installation packages. The file allocation table functions as a linked list that tells the computer which cluster comes next. If the table becomes corrupt, the operating system loses the link between the parts of a file. This simple design lacks the robust security features and permission systems required by modern enterprise environments. NTFS is the standard file system for all modern Windows operating systems, providing advanced reliability and performance features. It replaces the simple allocation table with a sophisticated database structure known as the master file table. This architecture allows for superior data management and faster search operations across massive hard drives. The master file table acts as the heart of the NTFS volume, containing records for every file. Small files can reside within the MFT record itself to provide near-instant access during system boot. This design minimizes head movement on mechanical drives and reduces latency for the user experience. One critical feature of NTFS is journaling, which records metadata changes in a special log before execution. If a power failure occurs, the system uses this journal to restore the disk to a state. This prevents the common data corruption issues that plagued older file systems during unexpected system shutdowns. NTFS also provides robust security through access control lists, which define specific user permissions for every individual file. Administrators can restrict access to sensitive data based on user identity or group membership within the network. This level of control is fundamental for maintaining privacy and security in shared computing environments. Additional features of NTFS include transparent data compression and encryption to protect information at the hardware level. These tools allow users to save space or secure their files without needing third-party software applications. The system handles these tasks in the background while maintaining high throughput for data operations. Linux systems utilize the EXT4 file system, which is the latest evolution of the extended file system. It is designed for extreme stability and can handle volumes up to 1 exabyte in total size. This makes it the preferred choice for servers and data centers that require maximum uptime. Instead of a master file table, EXT4 uses an Inode structure to store metadata and pointers. Every file has a unique Inode number that contains the owner permissions and pointers to the data. This separation of data and metadata allows for efficient file system checks and faster disk performance. EXT4 implements a feature called extents, which groups contiguous physical blocks together to reduce the metadata overhead. This improvement over older block mapping techniques increases performance when dealing with massive multi-gigabyte files. It also reduces fragmentation, which is a common cause of performance degradation over time. To bridge the gap between FAT32 and NTFS, Microsoft created the exFAT file system for Flash. It removes the 4 GB file size limit while maintaining the low overhead required for removable storage devices. It is now the standard format for modern high-capacity memory cards used in professional cameras. Cluster size selection is a critical decision when formatting a new drive for a specific data workload. Large clusters increase speed for big files but result in wasted space known as slack space. Small clusters maximize storage efficiency for millions of tiny files but can slow down the system. Slack space occurs when a file does not perfectly fill its final assigned cluster on the physical disk. The remaining unused bytes in that cluster cannot be used by any other file in the system. This wasted space can add up to gigabytes of lost capacity on drives with large clusters. Fragmentation happens when the file system cannot find enough contiguous space to store a file in one piece. The computer scatters parts of the file across different physical locations on the spinning magnetic disk platter. This forces the drive head to move more often, which significantly slows down data access. Defragmentation is the process of rearranging these scattered bits into sequential order to restore peak drive performance. This maintenance task is essential for mechanical hard drives, but should never be performed on modern SSDs. Modern operating systems handle this task in the background to ensure a smooth user experience. SSDs manage data differently than mechanical drives because they use flash memory cells instead of spinning magnetic disks. They utilize a process called wear leveling to distribute writes across the drive to extend its life. This logic is handled by the SSD controller rather than the main computer file system. The trim command allows the operating system to tell the SSD which data blocks are no longer used. This information helps the drive maintain high write speeds by preparing empty blocks in advance for future. Without trim, an SSD would slow down as it becomes full of old deleted data. Hard links and symbolic links are tools that allow one file to appear in multiple directory locations. A hard link points directly to the inode, while a symbolic link is a path to another. These features are used by the operating system to manage libraries and system dependencies without duplicates. Apple devices use the APFS file system, which is optimized specifically for flash storage and modern encryption needs. It features snapshots which allow the user to revert the system to a previous state after it. This copy-on-write architecture ensures that data remains safe during the update process on mobile devices. Advanced file systems like ZFS and BTRFS include built-in error correction to combat a phenomenon known as bit rot. They store checksums for every block and can repair corrupted data using redundant copies on the drive. This level of protection is vital for long-term archival of important digital records and photos. RAID configurations allow multiple physical drives to appear as a single logical volume to the operating system kernel. The file system manages data across these drives to provide either increased speed or better data redundancy. This technology is the backbone of modern server infrastructure and high-end workstation storage solutions. The boot sector contains the initial machine code required to start the file system and load the kernel. Modern systems use the GUID partition table to manage partitions and ensure compatibility with large hard drives. This standard replaces the older master boot record, which was limited to 2 terabytes of space. In our next technical lesson, we will examine the architecture of databases and how companies store information. We will explain the logic of SQL and NoSQL systems and how they handle massive data loads. This will show you how raw files evolve into structured and searchable digital assets.
The file system is the silent manager that keeps your digital life organized and safe from total chaos. Understanding these structures helps you make better decisions about data storage and computer maintenance for the future. Which file system do you trust more with your most important personal data and memories? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.